Hi Nicole, this is 6.8, and in it we want to find the orbital that the electron is coming from. This electron is in an excited state of the hydrogen atom. Now remember that for the hydrogen atom, the energy of the electron is only determined by the energy level, the n, the principal quantum number. Let's write some stuff down. So n is going to be the energy. It's going to determine the energy. So they have given us an energy here, 3.4 electron volts. Now I prefer joules. So I'm going to immediately convert this to joules. You don't, of course, need to, but if you also prefer joules, then yeah, it's that many joules in 1 electron volt. That's the definition. That is because this is the number of coulombs of charge 1 electron holds. We'll be using that charge of the electron number later without the energy units. But anyways, this is going to give me a certain amount of energy, which is 5.4 times 10 to the minus 19. So this is 5.4 times 10 to the minus 19 joules of energy. Now I'm going to use this to get what n is. All right. Now, how am I going to get what the L is? Well, the L is the orbital angular momentum quantum number. So it says orbital angular momentum is root 2 h bar. All right. So, So the L is going to be given by root 2 h bar. Now, how does that relate to the quantum number L? Because L, a quantum number, all these quantum numbers have to be an integer. They can't be root 2 times something. They have to be an integer. So in your textbook, where's your textbook? Here we are. So in your text, I think I have a different page of your textbook open already. Maybe this page? Is this what I want? Yes. So in your textbook, there are some, there is a nice little formula. They have already figured out for you the orbital angular momentum quantum number given an orbital angular momentum. And this is radial, this is still radial, so orbital angular momentum is not radial. It is the other part. It is the angular part. There's the full wave function. Here it is, angular momentum. So the total angular momentum of the electron is equal to h bar times the square root of L times L plus 1. So this is equal to h bar times the square root of L times L plus 1. I need to find what L is. Well, obviously, if L equals 0, then this would be 0, and that's not the case. If L equals 1, then this would be root 2, and that is the case. So L equals 1. We got that. Now remember, the meaning of the L quantum numbers is the orbital shape. So it's S, P, D, F, corresponding to those numbers, those L values. So obviously we have a p orbital here. That is a p. This means p orbital. Now the ML, on the same page of your textbook, so the ML is the magnetic quantum number, also known as the z component of the angular momentum of the electron. They call it the magnetic quantum number, M, because if you apply a magnetic field, the different M's, the different M's give you different energies. But under normal circumstances, and this is a normal circumstance, there's no magnetic field that is defined, and so we just ignore the different energies. The magnetic quantum number gives you, if it's a p orbital, it gives you the orientation. You remember px and then py and then pz, like coming out of the page at you, something like that. So it's the orientation. If it is the d orbital, then it's not just orientation. It's also there's some shape that is affected. You know, the d orbitals look kind of weird, and the f orbitals even look weirder. All right. So, anyways, the z component of the angular momentum is the given by the magnetic quantum number, and it says no component of angular momentum along the z-axis. So that means the z component of angular momentum is 0. So that probably means that the magnetic quantum number ml is also 0, but let's just make sure. Here we are. So the z component is equal to ml h bar. Okay, so we're saying that there is no component in the z direction. So 0 equals ml h bar. Divide both sides by h bar. Ml equals 0. All right, so there is no z component. So what we have so far is a p orbital and ml equals 0. Right now, ml for the p orbitals, it could be -1, 0, or 1. One of these is px, one of these is py, and one of these is pz. Which one is ml equals 0? Is it px, py, or pz? Let's look at the textbook again. Okay, so where can we find information about px, py, and pz? Let's see. It says that something was described in chapter... well, we're talking about p orbitals. So here we have s orbitals, and let's see if we can get some p orbitals down here. Here we go. Here we have some p orbitals. All right. We have already seen that the 2p0 orbital is the same as the familiar 2pz orbital, but the 2p plus or minus 1 orbitals involve blah, blah, blah. Okay, so we're not interested in 2p1 or 2p -1. We're interested in 2p0, which is what we have, and it says here that 2p0 is 2pz. Okay, so I'm satisfied that we have the pz orbital here. But let's figure out the n. Now, how can we figure out the n? Well, there are two ways to figure out the n. Let's look for the energies, because they have given us an energy, and remember, the energy is determined by the n for a hydrogen atom. It is not determined by the L or the M, unless you have applied a magnetic field or something like that. So let's find the energies in terms of n. There's a hard way to do this, and there's an easy way to do this, and they both give you the same answer, and the answer is not 2. All right? Let's start with the hard way, because that's the way that is given in the book in this particular chapter. Where does it say? Here it is, the energy. So this is the hard way. The energy is equal to blah, 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 with, there's an n here. Everything else in here is a constant. All right, now, I want to explain this hard way to you, just in case you need it for an exam. I have never seen this kind of thing on anybody's exam at any school, but just in case your school is weird. Z squared e to the 4th over 32n squared pi squared epsilon naught squared h bar squared. H bar squared? Yes, h bar squared. Okay. So I'm going to solve this equation for the n. All right. So that lets me switch places between the n and the e. So I get this e epsilon naught squared h bar to the 4th. And I take the square root of both sides. Now, the n is going to equal the square root of the mu. Okay, what is mu? Mu, remember, is the reduced mass. So it is mass 1 times mass 2 divided by mass 1 plus mass 2. In this case, we're talking about the electron, so mass 1 is the electron, and mass 2 is the nucleus. For a normal hydrogen atom, nucleus is the proton, so it's the mass of a proton. So this is mass electron, mass of the proton. Now, it says in your textbook that the proton is 1,836 times the mass of the electron. Right? So this now turns into mass of the electron times 1,836 times the mass of the electron, divided by mass of the electron plus 1,836 times the mass of the electron. Okay, so this plus this is 1,837 times the mass of the electron. And this times this is 1,836 times mass of the electron squared. So 1836 is almost the same as 1837. They're less than 1% different. In fact, I think they're like something like less than, well, anyways, they're almost the same thing. So for all practical purposes, they can just cancel out. Now, mass of the electron squared over mass of the electron is just mass of the electron. So that means mu is, I mean, for practical purposes, mu is effectively, how did this get here? Mu is effectively just mass of the electron. Right there, mass of the electron. So I'll write that in here. So this is negative the mass of the electron, which is 9.11 times 10 to the negative 31 kilograms. I looked that up on the internet because I couldn't find it in your textbook. Z is the atomic number, which is 1 for the hydrogen atom. So that's 1 squared, that's 1, and just ignore that. E is the charge of the electron, which is 1.602 times 10 to the minus 19 coulombs to the 4th power. Well, we're going to put this whole charge to the 4th power. And then divided by 32. Now, the energy here, En, that was given as 3.4 electron volts. However, I put negative 3.4 because this energy is the energy, this energy is defined as the energy which is released by the electron. However, in this problem, they have given us the ionization energy, the energy it takes to kick off this electron from its excited state. And so that's an absorption. So that means I need to change the sign of the given energy, which was positive, to negative in order to fit it into this equation, which is convenient because now I'll get a real number because dividing two negative numbers gives you a positive number. Now remember, I like to use joules. I like to use joules, not electron volts, because joules, so 1 joule is really 1 kilogram meter squared per second squared. So knowing this allows me to cancel units. I'm going to cancel kilograms out, and if there's a meter here, I'm going to cancel it out. There's some seconds here, I'm going to cancel them out. It allows me to cancel units properly to make sure I'm doing this correctly. And so that's what I've done. So to convert this to joules, I use this. I think I just did this at the beginning of the video, right? 1 electron volt is that many, not C, that many joules. It's 1 electron volt, so electron volts cancel. And remember, a joule is a kilogram meter squared per second squared. And then I put, there has to be a pi. I think this pi is supposed to be squared. Yeah, that pi is supposed to be squared. Sorry about that. That pi is supposed to be, it's missing from here. Sorry. Okay, so that pi is supposed to be squared. Sorry about that. Negligence. Right, so there should be a pi squared here. And then there should be, this is h bar to the 4th power and epsilon naught squared. Okay, so this is kind of long, huh? So epsilon naught is the permittivity of free space. So I have found that on the internet. It is 8.85 times 10 to the negative 12. And you see this is meters, this is kilograms, this is seconds, and amperes. Amperes is coulombs per second. This is coulombs squared per second squared. Okay, so these units are things that I'm going to cancel out because I've been using joules. Alright, so this is 8.85 times 10 to the minus 12. This is 8.85 times 10 to the minus 12. And this is epsilon naught squared. That's squared. And then h bar. Now h bar, so h bar is h over 2 pi. But I'm going to use joules here because I like to use joules. 6.626 times 10. So this is the hard way. We don't have to do it this way. Joules second, and this is to the 4th power, all right? And then I also have to multiply on this denominator pi squared. So I'm put 3.14159 squared. And when you do all this math and you take the square root of all of that, you get 6.3. So n is about equal to 6.3, but n is not allowed to be anything but a integer. I mean, in the case of n, it can't even be negative, so it has to be a whole number. And it can't even be 0, so it actually has to be a natural number. So we're going to say that n, we're going to round this to the nearest natural number, which is 6. So n equals 6. This is the hard way. Let me show you the easy way now. The easy way is to use the Rydberg equation, which we used in one of the first 3 problems of this homework assignment from a video that I made on a different day, several days ago. Remember, there was a Rydberg constant, and it is times 1 over the first energy level, the one that you end up in after an emission, minus 1 over the second energy level, the energy level that you're coming from before you emit energy. Right? So this is the Rydberg equation, and this lambda is the wavelength of the photon of energy that you emit because of this transition. So what is the transition that's in this problem? Which energy level to which energy level? Well, this amount of energy has to be absorbed if we remove the electron. So removing the electron means that we're starting at some initial excited state. We don't know what this N1 is. We're going to solve for this N1. But removing the electron means that the N2 is really infinity. Now, for all practical purposes, I mean, theoretically, this you do not do 1 over infinity, but for all practical purposes, 1 over infinity is 0, right? So I think we can just make this 0. So that means 1 over lambda equals the Rydberg constant, which is 1.097 times 10 to the 8th per meter, times 1 over n1 squared. We're going to solve for n1 squared. But what is this 1 over lambda? Remember, our energy was 3.4 electron volts, which is 5.4 times 10 to the minus 19 joules. Right? So that was the energy. So energy equals h nu, and c equals lambda nu. So if I solve this for nu and substitute that in there, I get E equals hc over lambda. Solving for 1 over lambda, I get E over hc equals 1 over lambda. So I'm going to plug this in for 1 over lambda, because that's what it is.
Yeah.
Yeah, hi baby. So the E here, is 5.4 times 10 to the minus 19 joules over H. This is the H. I'm using joules here. And C is the speed of light in meters per second. So seconds cancel, joules cancel. I just have 1 over meters now. This is 1 over meters. And that equals 1.097 times 10 to the 8th, right here, 1 over meters. So meters negative 1. So I'm going to... 1 over meter. Okay, so this is getting a little too messy. So I'm going to rewrite this, but I kind of don't have room. Okay, so I'm just going to cross this out. So this is all 1 over lambda. This is 1 over lambda, okay? So I'm going to calculate this out. Okay, so that's 5.4. Okay, 5.4 times 10 to the minus... 5.4 times 10 to the minus 19th divided by 6.626 E34 minus divided by 2.998 E8, and I get 2.7 million. So 2.7 times 10 to the 6th. So 2.7 times 10 to the 6th per meter equals 1.097 times 10 to the 8th per meter times 1 over n1 squared. And remember, I'm solving for n1 squared. So I'm going to multiply n1 squared on both sides. So I will get n1 squared here and n1 squared here. So these cancel. And then I'm going to divide both sides by 2.7 times 10 to the 6th. Divide both sides by 2.7 times 10 to the 6th per meter. Per meters. To get rid of this, get n1 squared alone. This is a negative 1. And then that's going to be, so this goes under, and this goes on top. So I get 40. So what's this? So the n1 squared ends up equaling 40. n1 squared ends up equaling 40. So that means n1 equals the square root of this. Square root of this is 7? Oh, it was 6. So I've done some rounding here. So when I did this originally, I did it without rounding. So when you do it without rounding, you get 6. Oh, wait a minute. This is E46. Okay, so here, let me try that again. So AC, clear this. So 40. And then take the square root of that. Oh, I used the wrong symbol. I don't know what this gamma is. But I should be using this guy. Square root of 40 is 6. Okay, so n1 equals 6. So both the hard way and the easy way, I get an n of 6. So I believe the correct answer is the 6pz. And that's it for number 6-8. The book said it was 2pz, but there's no way it's 2pz. The book said for 6-8, she said 2pz. There's just no way. PZ, yeah, but not 2. There's just no way that was 2. I did it both ways, the hard way and the easy way. You know, and I didn't show it in the video, but on a separate piece of paper, I canceled all these units out. All the units canceled out. So the n was correct. 6. There's just no way it's 2. I suggest you bring this up to the prof or compare answers with a friend. Thank you.